Welcome back, my structural analysis friends. One challenge that faces engineers as they perform an analysis or design of a structure is determining the worst possible loading configuration for a member or a structure. Where should loads be placed that produce the maximum effect? And in very large structures, this becomes a major challenge. One technique that we use to help us resolve this is a method known as influence lines. And influence lines cover everything from beams to girders to trusses. They have a whole lot of applications that greatly help an engineer make these decisions. So in this lesson, that's what we're going to look at. So without further ado, let's get started. So the first area that we're going to look at with regards to influence lines has to do with beams. And the way that we set these up is basically what an influence line is that it's used for showing internal effects, whether it's a reaction or an internal shear or an internal moment or anything within a structure at a singular point in the structure as a load is moved across the structure. So to kind of illustrate the idea here is that I have a simply supported beam and I'm going to place a unit load acting on top of this. The one kip load located at A1 from the left and B1 from the right. And so I could quickly, using basic static skills that we've reviewed in other videos, come up with a shear diagram that looks something like this. The value of the shear here is PB1 over L, and the value of the shear here is minus PA1 over L, and then the moment is PA1 B1 over L. And so this should be pretty basic. Okay, now if I take that same load and I relocate it to a new position, let's call it A2 and B2, the shape of the diagram still looks very similar, but the numerical values associated with these all change. For instance, the shear here is now PB2 over L, and then the one at the bottom is minus PA2 over L, and then the moment diagram is PA1 B1 over L. Okay, so that's our kind of approach. So what we want is now as a designer, I'm after the maximum value. For say the shear, the maximum positive shear, or maybe I want the maximum negative shear. Where do I put this load on this structure such that it gets me the right picture? It may be one of these two, or it could be a completely different one that we haven't even drawn. So we have to come up with a more general approach to be able to create this methodology, to be able to have a better understanding. Okay, and so what we're going to look at is basically we're going to plot our influence lines such that they plot the magnitude of a load at a given point versus the location of a unit load on the structure. So let's take and look at that in a more general sense. Let's take the same beam structure here. Okay, I have a simply supported beam. My unit load is now located at some position X. Before it was A1 in one spot and A2 in another. Now it's just an arbitrary variable that we're going to call X. And that's the heart of what we're getting ready to do. Okay, free body diagram is a reaction AY upward at the left and a reaction BY upward at the right. Okay, and so we know that for different values of X, we can create we can solve for different values. So suppose I want the reaction at AY. I could start out the load at 0, I could put it at midspan, I could put it right, and I could start to generate a plot of all of these things. And ultimately, we'd like to get to a point where maybe we could use some calculus to help us figure out what are the maximum effects and be able to work those things as well. Okay, so very simply, let's just take a look at the reaction at AY and how I would start to solve that. So if I took that same free body diagram, slide this over a little bit. Okay, and what we're going to look at is that if I wanted the reaction AY, I would sum moments at B, and that's this equation. I know I kind of jumped down here. We'll come back around. All right, so if I sum moments at B equal to 0, then that equation will be 1 kip times L minus X minus, that's an AY, a little fuzzy there, sorry about that, AY times L all equal to 0. And then if I solve for the unknown AY, I get a function of X. And that tells me that the reaction AY varies as X varies. So at X equals 0, it's a certain value. At X equals L, it's another value. And I can generate a table of data that does this. Or if you just want to use basic, algebra skills, you could plot this as a function. Okay, but I just chose to go ahead and do a table just to illustrate. So when X is equal to 0, that means that this point load is directly over the supported A. Okay, and so the value of the reaction would be 1.0. All that load from that point load would go straight into the support. Okay, now again, we're plotting data for specifically what's happening to AY. Okay, at L over 2, then you could plug in and you find out that AY gets a value of L of 0.5. And then when at X equal to L, when this load is over this support on here, all the load goes into B and none of it comes back to AY. Okay, and so that's kind of our general data if we wanted to. And so we can make a plot of this. And so for the reaction at AY, this is the influence for the reaction at AY. I would have 1.0 here, 0.5 at L over 2, and then 0 here. I'm plotting the value of these influence factors, this guy, versus its position of that unit load. And so when I do that, very quickly, you can see where the maximum is, okay, assuming that we're able to interpolate the data correctly. So here's 1.0 is the max. So if I wanted the maximum reaction at A, I would put a point load, located here. And you could go through and you could do the same thing for, say, our reaction at B. And that's not be a C, that should be a B. Okay, and we could go through and do the same thing. And if I write the equation in a similar fashion, the equation for BY then is going to be a value of X equal L. And I could get that by doing sum of forces Y equal to 0, upward positive is going to be equal to a minus 1 kip plus a Y plus BY all equal to 0 is my equation. And so if I take my equation of AY in terms of X and plug it in here, this is what I get left for BY. So BY is X over L. And so we could plot that guy. And if I do that, you see that you get a different shape. Now again, this is for the influence, an influence factor for BY. Okay, it's vastly different than the one that you saw for AY. But now I know that in order to come up with the maximum positive value of a reaction at B, I would want to put my load such that it was over the point load was situated directly over it. Because, when the point load is over this location, it's a value of 0. When it's at L over 2, it's at a half, so that's the L over 2 location. And then at L, it was a full 1.0. So that's and you can see that they're kind of inverses of each other. But now I have a way to be able to figure out where do loadings need to be in order to get me the worst possible effect, or I say worst, but the maximum effect at either of those locations. Now, this is a very simple example, and we'll get into some more complex ones as the problem starts to move a little bit forward. Okay, now, that was for external reactions. We can go in and we can look at, say, internal effects just as well. Okay, and so if we look, what we do is, suppose I want to find, I changed my nomenclature a little bit. So AY is here, okay, and its value is still going to be 1 minus X over L, and CY is still going to be X over L, okay? And then I have a point B in the middle, that maybe that's what I'm interested in. Maybe it's the location of a splice connection or something like that, to be able to do it. So I know that if I wanted to find the behaviors for the reaction at B, that I would draw a diagram that looks something like this, that I would cut it at B and expose all of the internal effects, and this is my positive sign convention. And the same thing works for moment. That I have a counterclockwise moment, a downward shear on the left side, on the right side of the cut, and then on the left side of the cut, it's the opposite. So clockwise moment, upward shear, and we're good to go. Now you'll notice the one thing that we have that we're looking at that I can choose to work off of either one of these pieces. I haven't put the 1 kip load because there's 2 possibilities that could happen. The first case is that my load case occurs, if I locate position B at some distance of what I'm calling little a here, okay, our intent is to make a plot that covers the position of this 1 kip load along the entire full length of the beam. Okay, so the first scenario is that the 1 kip load occurs between A and B. And if that's the case, I would get a picture that looks something like this. Okay, and this would be my free body diagram that generates that picture. And so I could do my equations, do sum of forces in the y direction. Okay, and so VB is equal to 1 minus X over L. This guy here is the AY. Okay, and then minus 1, and then minus X over L would be the value of the shear at that location. Okay, so it's a function of X. Okay, now the thing that we have to be careful of is that that's valid only on this interval, 0 less than X less than A, because that's where this picture was valid. Okay, and then what we can look at then is we can go in and we can look at the next one for when A, when it's between the two. And now in this case, what I've done is I've jumped over and taken the other side. So now I'm taking segment BC, which has the load. Okay, I could just as easily have set this up and done the same scenario as what I did before. So if I draw this in a little bit here, I have a VB here, an MB here, I have an AY here. Either one of those will get me the same equation, okay, where this would be the piece on the left from A to B, and now the load is off of it, okay, or I could be looking at the piece on the right where the load is containing the 1 kip load. It's one or the other. They will both get you the same equation depending on what you're after, what you're looking for. So a lot of times that's one of the tricks that we'll look at is how do we know what to choose? We choose the one that's simpler. So what you see is that the equation coming off of this equation is VB plus X over L, which was the reaction CY, minus 1, is going to be equal to 1 minus X over L. And if you look, you recognize that form. That was the equation for AY. Okay, so that was the AY equation on that. And mathematically, that should make sense by looking at the picture above, that I could say, oh, if I sum forces into Y, clearly VB has to be the same as that value. But the limit is that this is only valid when A is less than X is less than L. Okay, and so that's the game that we play. So we've got two equations, so we get kind of this step function thing. So if we plot this, and we plot our values, now this is the data that we would have for the first limit, where it was minus X over L. When X is 0, we had 0. When X was A over 2, it was minus A over 2. And when X was A, it was minus A over L. Okay, and likewise, for this one, it was when X was equal to A, which is our lower bound on the limit. Okay, it's 1 minus A over L. When it's half of that distance, L minus A over 2, it's 1 minus L minus A over 2, L. And then finally at L equals X equals to L, then we get a 0 value. Okay, and if I plot that, you get a shape that looks something kind of like this. And so it's interesting. This is the influence for the shear B. So it basically decreases negatively until the point that the point load is sitting just to the left of that point. I get this value, and as soon as I step over the point, it jumps. And you'll notice that the amount that it jumps, this difference on here, is equal to 1 kip. So that would be the amount of the point load. Okay, and so there's this instantaneous jump on shear. So shear diagrams produce some very, very interesting shapes, if you will. Now, suppose I wanted the shear just to the right of the support at A. Okay, because this was the location, light this up a little bit, of X equals to 0. This is when X was equal to L. This line here is when X is equal to A. Okay, that was the way that plot was generated. If I go straight to this point here, this line basically continues up, and you can see that it looks a lot like that reaction diagram for AY that we had. Okay, so what happens is as this thing starts to slide over, as I get further and further away, the shear at that location gets smaller and smaller and smaller associated with that. Okay, and so it's kind of an interesting little fact, but that's the way that you construct the moments. All right, so what we'll do now is let's take a look at an example. It's very similar to what we just derived, generically speaking, but this time we're going to put some values in and kind of help see what these shapes start to do. So again, I have a simply supported beam. Okay, it's A is the left support, B is some point in the middle, C is my roller. Okay, and so if we go through, we can solve for our reactions, and as you would do with a basic statics problem, so maybe I put a reaction AY here, and I put a reaction CY here. Okay, we could sum moments at C to produce my equation for the reaction at AY, and so as you might expect, we get the 1 minus X over, in this case, we had a beam that was 20 feet apart, it was 12 feet to B and 8 feet from B to C. Okay, and so as we would expect, this form takes on a 1 times 20 minus X over 20, gets me AY. This is 1 minus X over 20. So here L is 20 for our beam. So that jives with what we had from before. Okay, and so what happens is that at a distance of X equal to 12, we know that the AY parameter is going to be equal to 0.4. Okay, and so I can plot those in. We know that when X was 0, it was 1.0, and that's always the case. It will always be 1.0 when it's over the support that you're after, at least for external reactions. Okay, now, I can get values larger than 1.0, and that happens a lot with cantilevers and that kind of approach. So that's my, so 1 and 0.4, and then clearly the other value would be 0 out here at the end. Okay, so we're going pretty quick through this. I think this is pretty self-explanatory, but at least just give us a little bit more practice with some real numbers in this. Okay, so now I can do the same thing. If I want the reaction at C, I can sum moments at A. And so my CY then is x over 20. So again, this is that same form, x over L, that we talked about. Okay, and so my influence line for that, so at x equals 12 feet, at this location when the load is at B, then my CY value is 0.6. And what that means is that for every 1 kip of load that's moving across this beam, CY sees 60% of it. So if I had a 10 kip load here on there, then the reaction at CY when the load was positioned at this location will be 0.6 times 10 kips, or 6 kips. Okay, and then as it moves over, these values start to change, these coefficients. For shear, we do the same thing. This is dealing when 0 is less than x less than 12. Okay, that gets me that diagram. Okay, and so my VB then is going to be equal to a minus x over L, which is minus x over 20. And again, that's the same as a negative of the reaction at B. And then we go do the other side. Again, we're going fairly quickly through this because we've seen this. Okay, that now I look at the other piece for when x is between 12 and 20. And again, I chose to work with this piece because it had the load on it, but you could just as easily have worked with the piece over on the side, on the other side of the cut that doesn't have the load. It will get you the same expression. Okay, and that will be one of the things that we'll look at when we get into some more complex problems. And so my shear diagram then looks like minus x over 20 down at the lower end, and then at B, and again, this is at 12 feet. Okay, and this was located at 8 feet. Okay, and then as soon as I step over that point, it would jump up to 1 minus x over 20 on this particular case. Now, we could plug in x equals to 12 for all of these values, and you would get the 0.6 that we had before, and then we would get the 0.4 for the other case, and the difference is that is still 1.0. Okay, all right. But what I want to get into is how do we do for internal moment? Okay, so it's a very similar approach, so let's do that one. My camera to focus a little bit. Okay, so just like you did before, we're going to use the same free body diagrams for internal moment. So my free body diagram looks like this. Okay, when 0 is less than x is less than 12, we can sum moments at B. Okay, and we could write our equation. We know that this is 1 minus x over 20. And we know that for the whole length that was 12 feet. And so then this distance from here to here is 12 minus x. Right, and so we can do our basic statics and come up with our moment equation, solving for the internal moment here. Okay, and when I do that, you find out that the moment at B, the equation is equal to x times 1 minus 12 over 20, or that the moment at B is equal to x times 8 over 20 would be our equation. And so we can say, and that's only valid on that interval, 0 less than x less than 12. So I gotta be careful that it's bounded by this location, because that's the only moment I go outside of this range. When x is 13 feet, this load is now off the beam and the picture changes. So we have to be careful that that range represents this picture, generally speaking. Okay, and then to do the other half, just like we did with the shear, we jump over to the other side, and I do 12 less than x less than 20. And so that's the same picture. We got a moment that is now on the left end of the beam, so that's going to be clockwise positive. And we know that the distance, now the one thing to point out on this that's not real clear in this picture is that we're measuring everything off of a reference that we chose to be at the left end. So the value of the load, or the distance that we want, that x on all pictures is measured relative to the same reference. So if I draw this in here real quick, that off that red line there, but that's x. Okay, which means then that the distance from here to here, though, we know that at B, that's 12 feet. Okay, and so that becomes all of our pieces that we have on here. So then the distance here, and the hardest part is kind of getting these distances all figured out. But this distance is x minus 12. And so that would be the way that we would set that up. But again, you choose a reference and you draw it always measured to that reference, and it has to be the same for both. So even on the one that we just did up here, that was my reference. And notice that x was measured here. This was x equals 0. This guy is still x equals 0, and so forth. So you got to measure relative to each other to get that to work. And so once you have done that, then we can get our equation that this is 12 times 1 minus x over 20. Again, basic statics. You guys can work your way through that. And so then the moment at B then is 12 times AY in this case. If you notice, after I did the algebra, there's a little bit of shuffling that happened here. Okay, and so we can come in and we can start to plot our values for the different curves. So again, we're looking for the influence for the moment at B, which was at this location. From 0 to 12, it had a value of 8 times CY. Okay, which again, CY was X over L. Okay, and then we know that AY is 1 minus X over L. That's how we came up with these. So if we're looking at a position of 12, then I would plug in X for 12 and L of 20, and my value would then be 12 times that 0.4 value. Okay, and that gets me the 4.8 coefficient. So that means that whenever the moment is located, or the point load is located directly at B, the moment felt at that value is 4.8. When it was over here at X equals 0, the value of the moment here was 0, and whenever it's over here, the load is over B, there's no internal moment. And again, that's that same idea that point load, when it sits over the top of the support, will go straight into a support. It's not going to come into the beam, come over to the beam, and then go back. Okay, it's going to take the shortest way out of the system. And so that's how we can kind of quickly generate these moment diagrams for a singular point load. And it's not too hard. Like I say, but the thing that it does for you is it very quickly on this beam, I can tell exactly where I have to put the point load in order to get the worst possible effect at B. And that would be at this location where the coordinate is the highest value. Now, if you notice, it was 0 here. If I had a cantilever on this end, this line would continue down. And we'll take a look at one here in a second that kind of shows that, in which I could actually get a negative coefficient, and that's possible. So for reactions, most of the time, your values are between 0 and 1, but for moments, they never are, or almost never, I guess. I guess it's possible, but it's not very, it's very, infrequently does that happen. So that would be the case. But this is the ordinate. So if we knew that we had, a point load of, say, 20 kips that I had to put somewhere on this beam, and I needed to know the worst moment at this position B, then the moment at B would be equal to that coefficient of 4.8 times 20 kips there. It's just that ordinate times the value of the load that's sitting at it. Okay, and in which case that would then be 96 kips, feet. Right, and so those would be our units. So this has actually got a foot unit on it happening on that. And that's the way that you would get this very, very quickly, and by generating these diagrams. Now, like I say, we don't do a lot of this by hand, but what it does do, and we'll show you a method here in another video or two that will allow us to quickly construct these diagrams without ordinate values, and it will tell you where to place loads so that when you go to, say, a computer software like STAD or RAMSeal or whatever your analysis software is, RISA or something, whatever your software that you're using, you will know what load cases to put into the computer to guarantee that you get the worst possible effect as one of the results. Okay, because remember, in the computer software, we have lots of load cases and lots of combinations that we're dealing with. Okay, I don't really care what the value is per se, but I need to make sure that I've accounted for the worst when it generates those envelope drawings for us when we talk about those. Okay, all right, so that's kind of our moment approach. All right, so let's try another one. Okay, so for a cantilever, okay, we can kind of look at this, and so it's the same basic approach. I have a cantilever with a fixed end at the left, A, B, and C. B is located 3 meters from the left, and it's 8 meters in total length. The free body diagram for this would be the moment at A, AY up, and 1 kilonewton acting down. And so we want to find, what are our worst effects. So for us, so the influence factors for AY, if I do sum of forces in the Y direction here equal to 0, and we go up positive, then this is clearly AY minus 1 equal to 0, AY equals 1. Okay, and it's always that value for this free body diagram. Regardless of where that 1 kilonewton load is, all that load has to come back. It comes back over to this end. Okay, so AY is a 1. So the influence line for the reaction at AY in this scenario then is at X equals 0, it's a 1, at a half it's a 1, and at the very, very end it's a 1. And that would be our influence lines for Y. Okay, we can also do the moment, and this is where it gets a little different, okay? I know, and I'll explain why here in a second, but we draw our picture again, and again, we put our 1 kilonewton load at a distance of X, Okay, and I can solve for the moment at A in this. If I sum moments counterclockwise positive, sum of moments at A equal to 0, the moment at A is minus MA minus 1 kip times the position X is all equal to 0. Okay, and so MA is now equal to negative X. Okay, and so what happens when you plot this, and again, we're plotting X that way. Okay, and so at X equals 0, that was this one, and this was X equal to L, which we said was 8 meters, was that line. Okay, at X equals to 0, that equation tells me that the moment was 0. So we put a 0 point here. And then at X equals to 8, okay, it's now at a minus 8. So the way that we get the worst moment for MA is we put the point load clear out on the cantilever. That gets us the biggest load. Now, like I say, this one's a little interesting. It's almost the reverse of the shear and moment diagram. Because what happens is if I put the point load here at that support, it all goes directly into the support, and there's no distance associated with it, so the moment here is 0. Okay, whereas the reaction is still the 1 kip load. So that's it's this counterintuitive look. I think the first time out, I struggled with this when I was first learning this. It was hard for me to wrap my head around on this. Okay, and so that's what we have. So now let's suppose that we want to look at the internal effects. So this was for the support reactions, if you will, a support reaction at A for the moment and the force AY here. And then I can come in and I can look at, well, what happens? Say I want to find out what the effects are for the internal forces at B. And something interesting happens. So what we're going to do is we're going to draw our same beam. Okay. And we're going to look at figuring out, we know our equations look something kind of like this. That for our distance, when we look at the left piece, the whole thing, at B, for us, this whole distance here, for our example, is 3 meters. Okay, and so we're going to start measuring X from the support, the locator point load on this first piece. And just like we did before, we have to have 2 pieces on this. I'm going to do the case where 0 is less than X less than 3. That's my first case on there. Okay, and so now we play the exact same game. We know that AY is still 1.0. Okay, and then we know that if I say I'm after the shear on this picture, the shear at B, if this is 1 and this is 1, then VB is 0 on that interval. And that's kind of an interesting thought, but we'll decipher what that means here in a second. And then the moment, mathematically, I can solve for the MB value on this picture. So if this is X and the whole thing is 3, then this guy is 3 minus X. And so if I go through and I write my equation, and you solve for all of this and do the algebra, you find out that MB is also 0. Okay, and that's kind of unusual. So what happens is from A to B, there is no shear, at B. And from A to B, there is no moment at that location. And that should, while not completely intuitive, it should make sense. Because if you put a point load here, again, point loads are looking for the quickest way into the supports. And there is no support at the other end, so there's no reason for the load to travel this way. And so what happens if I have a load that's right here, it's going to all go over to the left into the support at B. And the same thing down here. Whereas if I get into a little bit of an effect here, for the other side, beyond B, then we can come in and calculate those values. So let's go look at that. And that's what this picture is here. All right, we're going to cut it at B and look at our internal effects. And so now this is the other side of the location I'm interested in. Okay, and so I know it's 5 meters to the end of the cantilever. Okay, and I have my 1 kip load here. The distance, again, we're measuring the distance back to here. From X is coming from support at A. Okay, and so from X, from here to the 1, so then it's 3 from here to my location. So the distance from the end of this region is X minus 3. Okay, and then the final end of it from here to the other end is 8 minus X. So if I take that free body diagram with these distances on it, I can now do sum of forces in the y direction equal to 0, upward positive. So on this picture, it's VB minus 1 equals 0, so VB is 1 kilonewton. Okay, and then the sum of the moments at B is going to be then minus MB minus 1 kilonewton times that X minus 3 dimension. Okay, and so MB is now equal to 3 minus X as our equation. But again, that's only valid on 3 less than X less than 8. That's where that picture was valid. So you have to have this piece of the puzzle on every equation that you write. So like on a quiz or a test or something, that's part of the answer because the equations change depending on where the load is, right? And so if I plot that, then from 3 less than x less than 8, the shear we said was 1, so it jumps to a positive 1 on the shear diagram from B to C, and it's constant all the way across. It's independent of x. Okay, so that's my shear diagram for this cantilever piece. And then MB would be 3 minus x when x is less than, or greater than 3 and less than 8. So at x equals to this location right here, that's x equals to 3. Okay, so then 3 minus 3 is 0. That gets me that one. And then 3 minus x when I get to 8 puts this guy out here at minus 5. And that would be our case here. So we know that to get the maximum moment or the maximum shear in this point on the beam, I would want to put the point load here to get the maximum moment, and I could put it anywhere to get the shear. Okay, that would get me the worst case because it's a constant shear on this cantilever. Okay, so I hope that made sense. Okay, all right, now let's go try one more. Okay, and this one, now we're getting into something that's a little bit more complex. Okay, we can do full systems. Okay, and so in this case, what I have is I have a multi-span beam from A, B, and C. Okay, and I have a hinge that's located at D. So there's an internal hinge here that breaks it, and then I have a roller at E. Okay, and so the first thing that I do is we look at I'm drawing a free body diagram. So now we're not worried about AX, but AY is up, CY is up. One kip is, somewhere along the top of this. And you can see that with that hinge, we're going to have to consider to the left of the hinge and to the right of the hinge. Every member kind of gets its own free body diagram, if you will. Okay, and then EY ends up being right here. Okay, so if we look at this, what happens is it turns out that our influence line for EY, if we were to sum all of this, okay, and then we were to try drawing our pictures on here, we would start out with pictures that look something kind of like this. Okay, and so the first scenario, when from here to here, when we're looking at 0 less than x less than 40 feet, okay, because my loads, if you look at it, I guess I didn't say that, I should have. It's 10 foot to B, 10 foot to C, 20 feet to D, and then 20 feet beyond. Okay, and suppose we want to find the influence lines for the reaction at EY. Okay, so the first case that we would look at is that we would have a 1 kip, our unit load, happening there, and that's located at a distance of x from here. Okay, and then the other picture that would happen would be the other side of it. Because the way we tackle frames and machines is we blow it apart at the hinges. The dy-ey picture looks something kind of like this. Okay, and so you can see that if I sum moments at this location, EY is 0 for all cases when the load is not on this piece, when it's between A and D. And so that's why we ended up with a 0 here. Okay. And then we could go in and we could look at the other piece, which would be the case where now I put a 1 kip load on this guy, and I measure back to A, and you can build just like what we did in the last cantilever thing, that it would look something kind of like this for the reaction at E. Okay, now, when I do that, you find out that EY is a 1.0. And that's interesting because, again, the idea is that if I put a point load over this support, say the 1 kip load is sitting here, is sitting over the support at E, then all that load is going to go into E. It should be a 1.0. Okay. And then and just realized that that's drawn backwards. Should be upwards that way. Okay, so it's the upward portion of it, not the lower portion. That out of there. Okay, because that should be a positive value when it's directly over 1. And then at any other location, like when it's sitting at E, it should be a 0 value because all the load goes into, C. And then when it's located at A, it should also be 0. So all of these supports, and we can quickly start building these values out. Okay. The rest of it, what happens in between is a little bit more, you have to do the math to be able to try to figure that out. Okay? All right. Now, if we go through, let's suppose that, and that's the way that we kind of constructed our EY pictures. If we go through, and here's all the math, and I'll let you read through this on your own. We've kind of explained it and gone fairly quickly on this, but that's the picture and the dimensions that you would use back here, let me put this back as x equals 0. So if you want to pause the video and take a look at that, that explains what I just verbalized for you. But let's go through and let's take a look at what's happening for the reaction at C. Okay, so for C, the picture we would look at looks something kind of like this, that we would have our effect on this. So if we come back and we look at when x is between 0 and 40, we would be looking again at this picture. Okay, now we already know that from this, that on this picture that EY was 0, okay, which then would make DY 0, which would then make this DY 0. Okay, and so now I have the ability to figure out this reaction, you know, if I'm after, say, the moment at C, or the reaction at C, then I could sum moments at A and generate that equation, that it would be 1 kip times x, and then divided by the distance between x and C. Okay, so that would be the equation that looks something kind of like this. And if we go through and we do our algebra, then it's CY times 20, okay, plus EY times 60 minus 1 times x, all equal to 0. We know that this guy is 0. When we did, the EY is 0, so that term vanishes when x is between 0 and 40. And so CY is then 1 over 20 times x on the interval 0 less than x less than 40. Okay, so now at x equal to 40 feet, CY then takes on, if I plug in 40 for this x, takes on a value of 2.0. And you can see very quickly that even though we're looking for the value of the reaction here, this is the influence for CY, that when the load is over C, it's 1.0, but when it's out here at the hinge, at the 40 feet, the last possible point, it's actually double that value. So the worst loading for him is when that point load is out here at the hinge, at this location. Okay, and then if you go through and you look at the other interval, we're now looking at a point load happening off of, say, this picture on here when x is between 40 and 60. Okay, well, we've got our equation for EY and DY, okay, which would then give me an equation that solves for this, if we look at that. Okay, and then once I have that, I can sum moments at A and include this guy in the effect, and that will get me CY. You get a curve that looks something kind of like what we have here. So that's how you quickly construct these pieces. And I know it's the first dose of this can be a little bit overwhelming, but we'll keep practicing, and we'll get it as we start to move forward. So anyway, I hope that's kind of made sense. So don't be alarmed that sometimes that influence factor can actually be much larger than 1.0 just because of these cantilever effects that are happening there. All right. Okay. Now, if we take that same picture and we look at AY, okay, from our picture, draw this real quick so that we have it. We had EY here, we had CY here, we had AY here, and again, we're looking at the one that's happening at some position X. That would be my equation there. Okay, and so the reaction generically, even though I haven't plugged in any values of CY and EY, static says that sum of forces in the y direction will be plus AY minus 1 plus CY plus EY all have to be equal to 0. So the equation for AY is equal to 1 minus CY minus EY. Okay, so when we are between 0 less than x less than 40, this equation becomes AY is equal to 1 minus, well, we know that CY had an equation of x over 20. We just solved for it. And EY had a 0 value because the load's on this side, and it did nothing to EY beyond. Okay, and so that gives me that AY then is 1 minus x over 20. So at x equals 0, AY is 1. At x equals 20, AY is 0. And at x equals 40, AY is actually a negative 1.0 on this. That's kind of interesting. Okay, and then for when we're between 40 less than or equal to x less than 60, if I plug in all the equations that I just had, you come up with an equation for AY that is x over 20 minus 3. Okay, but that's on the interval from 40 to 60. So if I plot these two pieces, okay, the first equation, this 1 minus x over 20, looks something like this, that it goes, and again, this location here, that's 20 feet. This location here, that's 40 feet. That we're at 1.0 here, I'm at 0 at CY, and I'm at minus 1 when x was equal to 40. That's all that equation is telling me. And then for the other side of it, when x is equal to 40, that becomes 40 over 20 is 2 minus 3. That's a negative 1. So that jives with this, and that should, for this, it shouldn't jump in this case. Okay, and then at EY, when x is equal to 60, because that's the value of the distance x here, I plug in 60 over 20 is 3 minus 3 should be 0, and that makes sense because, again, the point load sitting at the support, it's not going to cause a reaction over here. But these pictures can get very, very complex, and they can start to ramp up and become increasingly more complex. But now you have the ability to figure out, well, on my structure, maybe I'm looking for the case where the maximum positive load in this footing, or maybe this is a column in a building, that the worst loading for the compressive side of this column is when the point load is sitting right here. Okay, whereas the worst case for, if I put the point load out here, I could actually get a negative effect, which could be a tension or an uplift on that support coming here because of the negative one. And the value depends, if I put a 100 kip point load, say P is 100 kips, then the maximum compressive value is 100 kips. And when it's, then the maximum negative value is when the point load is over here would be a negative 100. And you would have to design for both the positive and the negative based on this load, because the load actually flips the signs of this, of this reaction value at AY. And so that's what the power of these influence lines are, is they quickly tell you where to put loads on your structure to get you the largest effect, whether it's largest positive or largest negative. And so that's how we do it for reactions. You can do the same thing for shear and for moments, and we'll do a lot more complex structures as we move forward. That includes, we'll be looking at girders. We can do this for trusses. Any structural system you can do this for. And it takes a little bit of analysis. Now, again, it's a lengthy process. It's not hard. It's just kind of long. And we'll show you in the next lesson a technique known as Muller-Breslau, which allows us to quickly construct these based off of some simple rules that we'll define. So anyway, I hope that's made some sense to you. We'll take a look at exploring influence lines for the next couple of lessons, probably 3 or 4 more videos on this topic, and we will go from there. So as always, leave us some comments down below. Let us know if everything makes sense. If it doesn't, let us know what we can do differently, and we will be glad to help you out. So anyway, have a great afternoon. Happy engineering.